Assalamu alaikum everybody. This is task 2 for Fundamentals of Mechatronics. Today we are going to talk about analog to digital converters, digital to analog converters and sensors. So today we are going to talk about these topics over here. Let me put the pen. Now, what are the course learning outcomes? The course learning outcomes are perform analog to digital conversion systems, digital to analog conversion. We need to understand what they are. What do we mean by signal processing techniques, and assess the importance of sensors, and talk about how to drive the sensors and actuators. So this is mainly our topic in this task. Now the task will go as follows. First we are going to talk about analog to digital converters, then digital to analog converters, and finally we are going to talk about some electrical sensors. This task will have at the end a test which will be uploaded to SULMS. So first of all, let's understand what's an analog signal and what's a digital signal. An analog signal, directly measurable quantities in terms of some other quantities. For example, the thermometer measures the mercury height, rises the temperature as the temperature rises. So the car speedometer, which measures the speed of the car, the needle moves further to the right as you accelerate. The stereo volume increases as you turn on the knob. Digital signals, on the other hand, they have two states which are 0 and 1. So it's not an analog value. You cannot change it. You either have 0 or you have 1. In terms of analog, you will have different readings which are continuous. For example, the light switch inside your home is on or off. Door to a room is either open or closed. These are all examples of digital systems. Now, when we talk about analog to digital converter, the real world data is analog. Now, this data, in order to be processed by a microcontroller or a microprocessor, it needs to be a digital data. So we need to understand how this process is done. How do we do this process, changing an analog signal into a digital signal? So we need to convert these analog signals into a digital representations so the microcontroller can use it. The process of converting analog to digital includes two steps, which is sampling and holding, then quantization and encoding. What do we mean by sampling? Consider this analog signal in green. If we want to convert it to digital, we need to take samples at some interval times over here, at a constant interval time. The smaller this interval time, more samples we get. More samples we get, the better our digital signal represents our analog signal. So if delta is the time interval between two consecutive samples, then the sample time can be represented as h of n is equal to h delta of n. Now, h of n is our analog signal, and h of delta n is our digital signal. Consider the analog signal x of t that can be viewed as a continuous function as shown in this figure over here. The x of t can be represented as a discrete signal by using x of t at nts interval to form x of n. Instead of x of t, we get x of n, where n is the sampling period. The sampling rate depends on time. 1 over time is equal to frequency. So usually we specify the sampling rate in terms of frequency. So f of s is equal to 1 over t of s, where f of s is in hertz. So in order to regenerate any signal, we need to satisfy the Nyquist rate that states that f of s, which is our sampling frequency, should be twice as the maximum frequency that we are sampling. So let's say I'm sampling a signal which is running 1 kilohertz. My sampling frequency needs to be at least 2 kilohertz for this to happen. Next step, after you take the samples, you need to quantize them or give them a level. Then that level will be encoded into a digital value. So we have quantization and encoding. The resolution Q is defined as the full scale range of the analog to digital divided by the number of outputs. So we have a resolution Q, which is equal to V max, maximum voltage over here, you see it, minus V minimum divided by 2 to the power n minus 1. So if n is equal to 3, 2 to the power 3 is 8, minus 1 is 7. So you see here 0, 1, 2, 3, 4, 5, 6, and here is your 7. Now, where is n important? N is important in many places. When we talk about the resolution, if you go and buy a TV, which is a standard definition, it will have less pixels inside the picture. If you go for high definition, it has high resolution. High resolution means it has more pixels, more information in each, more pixels in each inch. Now, some concepts and terminologies when we talk about analog to digital converters. Offset is the minimum analog voltage. Usually it is 0 volt. Span is V max minus V minimum. So here, this is the span. Quantization is equal to span over 2 to the power n minus 1. Then we have V step size, which is equal to span over 2 to the power n. So step size is also the resolution Q, plus 1, of course. So step size is 2 to the power n. Here it is 2 to the power n minus 1. Remember the difference. Resolution is the number of bits in the analog to digital converter. Also the smallest analog value that can be changed. So the conversion, if we have an analog value, it is equal to the digital number multiplied by step size plus offset. This will give you your analog value. If you are given a digital value, you can get the analog value from here. A digital number, on the other hand, is equal to the analog number minus the offset divided by the step size. You can convert between the two values if you know the step size and the offset. Examples of analog to digital converters. In this analog to digital converter, we are using the parallel encoded flash ADC design, which provides fast analog to digital conversion. Now, first of all, this is a comparator. This triangle is a comparator which you studied with Dr. Mahmoud in instrumentation. Now, what does a comparator do? If the positive input is higher than the negative input, then your output will be 1. Else your output will be 0. This is a 4 volts and this is a voltage divider. So after the first kilo ohm, this will be 3 volts and this will be 2 volt and this one will be 1 volt based on voltage divider rule. So if my analog input is, let's say, between 4 and 3, then the output here, if my analog input, let's say, is 4 or 3.5, let's say my analog input is 3.5, okay, let me fix this one. If my analog input is 3.5, I will write here 3.5. What will happen? Here is 3. The analog input is 3.5, so this comparator will be high, and this comparator will be high, and this comparator will be high. Now, this is a decoder. The decoder will have 3 inputs here. Of course, it needs a 4th input which will be connected here to ground. Okay. Now, the 4 inputs, if the most significant one is 1, the output will be 1, 1, and so on, depends on the inputs. So let's say that my value over here is not 3.5. Let's take another example, and my value here is 2.5. When it's 2.5, then When it is 2.5, then what will happen? We are going to take 3 point, which is greater, 2.5 or 3? 3. So this one will be 0 and this one will be 1, and its output will be appearing on the decoder. Now this is the fastest analog to digital converter. It's called sometimes the flash ADC. Needs 1 clock cycle. So this is a very good circuit. However, it's very, very expensive because you need a lot of components. The second type is the successive approximator analog to digital converter. The successive approximator analog to digital converter is quite simpler because you don't need much components. However, you need to understand the operation. So first of all, I will put my analog input through this value over here. Let's say my analog input is 3 volts. Okay, so here the start signal, I start my values, and the successive approximator will have a V reference. Let's say my V reference is 5 volts, which is this value over here. So the first output of the successive approximator, this is a 4-bit successive approximator. The first output will be 1, 0, 0, 0. Now convert this into analog value. How do I convert this? Go back to this equation over here. What's the analog number? I have the digital number, which is the analog number, which is 8, and the step size, I know it from here, which is the span over 2 to the power n. Span is 5 minus 0, so 5 over 8. You get the values. Then you are going to find the first value. The first value will be 2.5. Okay, the first value will be 2.5, which is half of V reference. Is 2.5 is 3 greater than half 2.5? Yes, so I will keep this value as 1. Next, we are going to change the second bit. Going to change this bit into 1. Okay, so when we convert this one, it will be 2.5 plus 1.25, it will be 3.75. Is 3.75 greater than 3? Yes, so this value will have to be a 0 once more. So this one, we will give it a value of 0, and we will go to the third one and so on until we convert. Now this converter is quite fast. See here, half of the maximum voltage, 1/4, 1/4 plus 1/8, and this one will be 0. So if this is 5, this one will be 2.5, 1.25, 0.6125 as our values, and you can find your output. This successive approximator is good. It will take around n number of bits cycles to convert the value, and it is very commonly used in many applications. So this is analog to digital converters. The next part is how to convert from digital to analog. So if I have a digital value, which is binary numbers, how do I convert it into an analog value? In order to do that, we are going to study 2 circuits. These circuits are the binary weighted analog to digital converter and the resistor ladder analog to digital to analog converter. So first, the binary weighted ladder. The binary weighted ladder is based on this circuit over here. This is our amplifier. The output of the amplifier will equal to minus V1 minus V2 over 2 minus V3 over 4 and so on. So I will put my bits over here and calculate V out through the value. Now the problem with this circuit is the value of R. Let's say R is 1 kilo ohm. Okay, R is 1 kilo ohm. So this resistor will be also 1 kilo ohm. This one will be 500. This one will be 250. the next will be 125, the next will be 62.5, the next will be 31.125, and so on. As you increase the number of bits, the resistor values become difficult to find. Plus, if this one is 1 kilo ohm, it will have tolerance plus minus 10%. So it will be between 900 ohms up to 1100 ohms. You cannot get the exact value. Exact value resistors means very expensive resistors. That's why this circuit is quietly not that often and used. The second part is the ladder circuit. Now the ladder circuit is quite a simpler one because you need only two values, 2R and R. Here is 2R and here is R. R, let's say R is 1 kilo ohm, then 2R is 2 kilo ohms. 2R, to get the equivalent of this circuit, 2R, and this one is connected to ground, this one is connected to ground, this is a node. 2R in parallel with 2R is R, plus R is 2R, in parallel with 2R, R, and so on. You get the equivalent resistance as R at the end from this circuit. This circuit is quite simple. You can see you put the voltage here, and as you move, the current will split itself. We are splitting the current here based on the current divider rule. So this is 2R, and all of these will be 2R. So the current will split in half over here. The result then will split in half over here, and so on. The current will keep splitting in half at each instant, and we just need to calculate the voltage using the equation for the amplifier. So the resistance between a node V0 and the ground is R, since it is parallel to the combination of 2R. So the first value is V1 is equal V2 over 2, V2 is equal to V3 over 2, and V0 is equal to V3 over 8 or Vs over 8. Remember, we just need to find two values of resistors. This makes this circuit very important. Now, we are talking about analog to digital converters and digital to analog converters. But where do we get the analog signal from? We get the analog signals from the sensors. Sensors, we have many types of different sensors. You have distance sensors, movement sensors, stress, strain, force, temperature sensors, many types of sensors. Here we are discussing some types of these sensors. The first one is the potentiometer. As you can see here, it's just a variable resistors that changes when you change the displacement or distance. Where we can find this one? If you know, when you increase the volume in your stereo, you can find this knob which increase the volume in your stereo, which is a distance sensor. Movement sensors, such as the velocity sensors, these movement sensors are based on Doppler effect, which says that the frequency changes depending on the speed or the velocity of the object. If you ever stood in the road and a car was horning while it passes, you hear the horn of the car changing as the car is moving. So this is not because the horn sound is changing, no, but because the speed of the car is changing as it's moving towards you. These are mostly used in the radar, which the police use to get the speeding cars. They use the Doppler effect. Next one is the magnetic sensors, which utilizes the magnetic phenomena. As this object moves, we are going to have changes over here in the value of the voltage and current because of the windings and the induction between the two state, the secondary and primary parts of this displacement sensor. The third type is the strain gauge, which is used for measuring weight. So the strain gauge is a measurement of pressure. Once you put some pressure on the strain gauge, the voltage will change, and the strain gauge will give you a different values and different outputs. Then we have the piezoresistive sensors. This sensor is changing on pressure. Once you apply a pressure inside over here, the diaphragm will change the strain gauge, and the strain gauge will change the value in the bridge over here. The third type is the ultrasonic transducers. These will send sound waves, one transmitter and one is a receiver. One will send a sound wave, the other will receive it, and then the change in the frequency will be measured to get the to calculate the time taken. If we know the time and we know the speed of sound, then we can find the distance very easily. This is mainly the task 2 information. A task assessment will be posted for you. You need to answer it. You need to study good, and if you need any questions, I will be happy to help you and assist you in any way that is possible. Thank you. Stay home and please stay safe.